Hi everyone. This week we're going to talk about energy units and consumption and go over ways in which you can convert from one energy unit to another if you're trying to calculate equivalencies in energy usage and output. So this sheet will become your friend over the next week. This essentially has all of the forms of energy units defined and their equivalents on the right-hand column. And this will be handy when you do your assignment number 3 and you're converting your energy sources. So like we'll be taking things that are in, say, BTUs, which is commonly used in heating and cooling systems, like your furnace operates in BTUs, and we'll give you, say, convert this amount of BTUs to kilowatt hours. So you'll refer back to the sheet to say, oh, okay, well, based on this, I can see that there are 0.00029 kilowatt hours in one BTU. And we'll go over that a little bit more towards the end of this lecture. But just so you know, this sheet is its own standalone PDF file also on D2L. So you can have that open and you can print it out so you can refer to it as you do your assignment. But just to quickly go over some of the things that you should be familiar with for your quiz and for the assignment. Joule is just a basic unit of work, and that is probably more used in physics realms more than actual practical applications. Kilowatt hour is what you see on your electric bill, and that's how you are charged for your electricity use. BTU, as I mentioned, is something commonly used in heating and cooling systems, and technically the formal definition is it's the amount of energy needed to heat 1 pound of water by 1 degree Fahrenheit. And an ampere is a unit of electric current. Watt is just a unit of power that measures the rate of energy conversion. So if you look at the equivalent for a watt, you can see it's 1 joule per second. So it's 1 unit of work per second. So a watt is technically a rate. It's not just a unit. A volt, you can think of volts as, a 3-volt battery. It's just the unit of electric potential. Horsepower, you're probably very familiar with if you're a car person in any sense of the word. Horsepower is the equivalency for horsepower is 750 watts. And then calorie and kilocalorie at the very bottom. The important distinction here is that the calorie with the lowercase c is the amount of thermal energy needed to raise the temperature of 1 gram of water by 1 degree Celsius at a pressure of 1 atmosphere. And so that is quite different from the capital C calorie, which is what you would be reading on the back of a food label, because that's food energy. So capital C, food energy, lowercase c, thermal energy. So the equivalency for a lowercase calorie is 4.184 joules. So that's an important distinction to note. So now let's talk about some sources of energy. The first one is natural gas. Many of you might heat your homes with it or use this for your stove or your dryer. It's a therm is how they sell natural gas, and it's a volume of 100 cubic feet. It generates electricity. It's used in industry to provide power. As I mentioned, heats houses. It's found underground, and so as such it's a finite resource, right? It's cheaper than oil. It's easier to transport, and one of the downsides, of course, is that it leaks methane into the atmosphere, which, as you may or may not know, we don't actually need more greenhouse gases, but that's one of them. So, but it does provide energy for countless thousands of people, so it's kind of important. Next is electricity. As I mentioned, it's sold in kilowatt hours, and electricity comes from, it's not just from a power grid. Someone has to power the power grid, right? So the way power gets to us through electricity is by fossil fuel combustion. Often coal combustion is generating electricity. Wind power is kind of a more recent development, harnessing wind. You may have wind farms actually in your area. And then there's hydropower, which is harnessing river flow essentially to generate electricity. And the problem with that is that you can't store it, so it has to be constantly generated. Just to talk a little bit more about kilowatt hours, again, this is kind of a unit with an energy source and a time. So this is how you calculate your kilowatt hour. Kilowatt hour is just your watts times multiplied by your time in hours, and then divide that by 1,000. I think you have a few of those on your assignment to do, actually. So another form of energy is heating oil. It's sold in gallons. It's pretty similar grade gasoline to petroleum, rather, sorry, to diesel fuel. And it's stored in storage tanks, and at least in the Portland, Oregon area. In order to sell a house in this real estate market, generally speaking, you have to decommission your heating oil tanks because no one really wants to heat their house with oil anymore if they can avoid it. So kind of becoming, I think, an outmoded form of heat and energy. Gasoline, pretty straightforward. I'm sure we all use it in some capacity. Obviously sold in gallons. It's a higher grade of fossil fuel than, say, heating oil or diesel for truck use. In the United States, we blend a lot of the gasoline with ethanol. And perhaps the most important statistic to remember from this particular slide is that the United States accounts for 44% of the worldwide usage of gasoline. That's a lot of gasoline. Another form of energy is wood, and it's sold in cords of wood. 1 cord of wood is 250 copies of the Sunday New York Times. And that's probably meaningless to some of you because you don't. I wonder how many of you have read the paper recently. I haven't read a newspaper in forever. I get the New York Times online. Anyway, forested acre produces 10 to 15 cords of wood. And so the variability in the type of wood will change actually how much energy you can get out of it. So if you have obviously higher water content, you're going to get more steam and less energy than if you have drier wood and more dense wood for that matter. So this is just converting everything into BTUs. These are all the equivalents for the other energy units that we talked about. And then, as I mentioned before, 1 calorie, the capital C calorie, is the food energy calorie, if you recall. And you can see at the bottom of that list there, 1 short ton of coal is equivalent to almost 20 million BTUs. So that's a lot of BTUs, and that's one of the reasons why coal is used in many parts of the world, and especially in developing countries. Coal is being used more and more to generate electricity as those countries develop and become more industrialized. This is just a snapshot of a Northwest Natural energy bill, just to show you they're selling therms of gas 79.3, and this is just the cost of it. This is not my bill. Just FYI. And then, oh yeah, and then this is just an energy meter example, kilowatt hours. And it's kind of interesting to see the energy use charge is different from the transmission charge, which is different than the distribution charge. So you have to pay for it in multiple ways, right? So what I'd recommend that you do now is you go to your D2L week 3 folder and download assignment number 3, download the worksheet that has all of those equivalents on it, and just knock that out. And please email me if you have any questions. I'm also going to start a discussion board, so if people are having trouble doing the conversions, they can kind of ask for help there. And then I'm also posting a really helpful short video on how to do conversion calculations, because if you haven't done these in a while, or ever for that matter, they might feel a little intimidating, but if you watch this video, I promise it will make it quite clear. It's really pretty straightforward. So again, have a good week, and I'll talk to you soon.